Hello and welcome to another video where I'm going to be talking about reverse engineering H1N1 loader. Was pretty prominent in 2015, I think. Don't really know too much when it comes down to the timeline of it. I do know that it was sold at some point, and no, it isn't Hack Forums malware. But basically what I'm going to be talking about today is import hashing. I believe, when I was doing this research, when I looked at the way that this worked, I come across the Cisco research, and it annoyed me a little because basically I'd done all of this sort of analysis. This happens quite often. I'd done all this analysis and I could have just Googled and looked. But there are bits to it which it doesn't discuss, and also it doesn't walk it through. It sort of just discusses it in a very general manner. So the Python script that they wrote actually looked good. I didn't actually run it, so I don't know if that works fully. The rotations to the left are 7 on theirs, I think. And on this sample it's 3. So this is a H1N1 loader sample. And basically they've done an interesting way in loading the APIs that they want to call. So if we look at build, which is, would you believe it, the actual build for the H1N1 loader bin. What am I doing? I'm in the wrong area. If we look at the import directory, we see literally nothing. There's nothing going on there. And you might be like, well, that's not how that works. And if you actually look, there's pretty much nothing there in all of these. So that's quite questionable. And if we actually, I don't know if CFF Explorer is going to actually identify this. The identifier that I have on another, no, it isn't. This machine is quite old when it comes down to analysis, but essentially this looked like it was not handcrafted, but used MASM or used something. It didn't use C language or anything. It did look like they had a relative understanding of assembly. So it became quite interesting. Actually, I shouldn't have closed CFF Explorer. If we go to the hex editor, could have used HXD to be honest, and we go right down to the bottom, we see these here. See, that's an interesting sort of, if we look at these, they're sort of left to their own. I guess if you haven't done reverse engineering, that doesn't look too strange, but especially in them sizes, that comes across as resources of some kind. If we go to the resource editor here, we don't identify it, but it's quite obvious that these are somewhat something to identify or look for later on. And COD6D616 we will hopefully see at some point. So if we just call and go here, essentially what we're going to find out is that this call identifies where the kernel is. And this will eventually, if you look here, the rotation of the left, this is actually the hashing here, and we'll see that in a moment. If you see, this will jump back here, around here, but we're going to do an analysis of this anyway. But we start here, it rotates, and it has a fixed size. That's the difference between this from the strings. So if I go into my notes here, we'll see that all of these are in the H1N1 loader, and this is what it actually gets from understanding the hashing of, we'll see in a moment, but it translates the content that we have in the executable down at the bottom here to APIs that are here. So essentially it will exhaustively search the address names within kernel 32 until it reaches a value that is the same as one of these, and then transfers the string of that value, which is one of these, and we'll probably call it late. Well, probably it will call it later on. Now, the reason for that, I've already talked about imports and API calls in another deobfuscation, API banker, is that obviously some of these aren't exactly great for it. So read process memory, it's looking like snapshot I think is here as well. So we're going to be enumerating and looking at processes, allocating memory, not that much. That's actually quite interesting. Create file, create process, create thread, wait for single object. So there's some, to be honest, there's not that much in regards to very malicious, except from reprocessed memory and the the process enumeration. But still, obviously they want to keep this to a low key sort of deal. And actually, it's kind of interesting as well how they did it. So what we're going to do is we're going to not go straight to where I set the breakpoint. That's where the strings are converted. We're going to go into the entry point. So they're all in this call. And we can see from here that pretty much you don't see this from a compiler whatsoever. This is obviously somewhat someone's built this quite well. So yeah, let's deep dive into it and have a look at what they're doing. So I have transferred into x32, x64 DBG, open source, and I quite enjoy actually the actual interface and everything about it. The amount that we've got on the side here, actually the layout as well is actually quite nice. It's not as annoying as Ollie debug or immunity debugger. The dumps as well. It just seems to have it's nicer, you know. It seems to have worked out for me, so I've left it at that. So yeah, I've transferred from here. I can't remember if I've done a video with it. I know I did screenshots with it, but yeah. So this one here is going to call and look for the address of kernel. If we get process hacker up and look at the build, and kernel 32 is always within a process, from my understanding. So whatever you do, you will always have kernel 32. So if we go, yeah, so there you go. So we're going to be looking at 7C8000. Is that 8,000? No, it's definitely not 8,000. It's 800,000. But 7C8 is what we want to look for. And they're just taking the understanding that kernel 32 is always going to be within a process, and also load library I assume was within that as well. Yeah, load library. So then you can go further and build upon it, but from static analysis you virtually have no imports whatsoever. As I said, when I looked into here in CFF Explorer, if we were doing a static analysis without looking at the actual values here, not there, that's zeros, all the way up here, if we didn't look at that and we simply looked at the data directories, we'd pretty much be dumbfounded in doing a lot of analysis, to be honest, because the values are set as 0. So what I'm going to do is I'm going to step over this, and we'll see there it hits on the return value 7C8000, and it does that by, if we go into this, if we look this FS, and this will be talking about the process environment block, which FS30 is. That's the identifier that allows us to see this, and then it'll walk through trying to find the certain value which holds the address value. Now, a lot of shellcode exploitation, that sort of area, do something like this, where they might want to know the kernel 32 address to do this exact thing, to call something dynamically. I can't say I'm too clued up with exploit development too much yet, but that is something that they do. So if you were a little bit unsure why there's a D-word pointer to FS when you're used to a DS, it's because of process environment block, essentially. We do see a load string here as well, so you can sort of assume what it's doing. I sort of half want to go back to show you what it's doing, but I am aware that it's 9 minutes. I'm gonna... No, it's not that interesting, to be honest. It's just walking through it. We don't need to. So then we go from these locations and we load the effective address of that. So let's go past that. So ESI is 40612. Yeah, so if we look there, this looks similar, doesn't it? So I talked about the CO D6 D616. That's exactly where that is, and that is actually going to be called, I assume. The boundaries are actually going to be, if you look at the value there, we see B4, so that will probably be there or there. I can't fully remember. It might be, yeah, there we go. Oh, wow. Okay, I could have just done that, couldn't I? I could have looked at the address there and saw B4. Anyway, so that will be the boundary. FF0, I think, is actually called in this for a check for the boundary limit. I can't exactly remember. But yeah, so these are basically set as the boundaries for what to look into. So soon we will see that C0, D6, D616 is actually put into a register, and we'll start to do this, which will be looped. As we can see, the jump not 0 is that one. That's not the one I'm looking for. Is that one, which will just go through this, increase the counter, and then compare. You know what? I'll go through it when we get to it, essentially. But so we've got to the. I've not done really well on time, but essentially we've got the kernel address there, the base address, and we're going to go into push it. We've got the boundaries for the actual the APIs that are within this binary, essentially, is what we've got. And we're basically going to, these are all hashed, essentially, and the reason for that is they're all set to 4. So you've got API calls that are obviously much longer than this, but can be represented with this in an easy way, and you'll see that in a moment. Push EBB, is that anything interesting? It might be, but we're not going to worry about that. I think that's restoring a value for later on. So we've moved EAX, yeah, we're just pushing it to somewhere. So that's used for something else. It's been pushed to the stack to be used for later so that EAX can be moved by EBP. EBP now has that kernel 32. Then we move, oh, you can read, I guess. Let's just step over for a while. We're actually going to get something from EDX, which is PE. We're actually going to be looking for the exports of kernel 32. Oh, I didn't get kernel 32 ready. Just give me one moment because this will take some time. To be honest, didn't take that long. But anyway, if we open this out with, could have just put it in the other tab. That's just wasting resources. There we go. If we go into the export directory relative virtual address, it's 262C, which is what it would be. So if we just keep going, 262C, and then it will search for the address of names from there. So we've got the relative virtual address, and now if we go into the export directory, what we're looking for is address of names, so 353C. So essentially it's just searching from that, so it got the address from that process, and then it's just working its way through trying to find, eventually being able to call and look at these names. But right now it's going to go from the address of names. So was it 353C? I've got my face in my way. 353C, yeah. So relatively similar. So let's carry on. Okay, is added on. And then we see that return to 353C, so it's searching for that. And then we will see in a moment, as we see we've got the rotate on the left, we will see, I think in that one, in ESI, am I right on that? Yes. Yeah, is that we will see the API name soon. So we added that on, we clear ECX for later. And then no, oh, COD, that is, sorry, yeah, ESI is being used for the, talked about this, for the actual hashed or the hash of the API. So we're going to use that as a comparison. And EBX, I assume then, will be the API. No, I'm wrong. 4BA5 is the starting point. 4BA5 will be, yeah, we're going to have to load. 4BA5 is the relative address name for it, but the actual name is then put into here, I believe. So let's have a look. Yeah, so there we go, EDI. And with that, we move on to our next bit, which is we are going to be hashing it. So let's just push EDX, which is probably being used. Yeah, EDX is being used. That's why it's being pushed to the stack, because EDX here is going to be used later on. So we need that for later. But so we then clear it, and then we're then going to rotate left. This is actually useless at the start because there's nothing in EDX, but that does come into play later. And then EDI is going to be referenced with DL, which will be nothing right now, obviously, because it's cleared. But then we increase it. So if we see, we've only got the A there. And I know I'm doing this at a slow point, but I'm just explaining this at just this point right now. Trying to get every minute detail, because it's interesting, actually. So then we're going to increase the counter, EDI, so that we can compare if it's 0, which it's not going to be because we're not at the end of the string. So no, we're good, thanks. And then we're going to come back again, and then once you notice the transformation, so we're rotating it 3 times this time, so we see completely different now. Crazy ASCII character, and then we're going to again XOR this with the letter C, I believe, and then we're going to again compare. We keep doing this, and active CTX is obviously not within. The first one is close handle, I believe. So yeah, it's close handle. So I'm just gonna, because we're on the 18-minute mark, I'm just gonna show one of these. So C16 was it? C0 D6 D616 is what we're looking for on the close handle. So if we go to, I've set that, so it's been set. And yeah, I'll just keep going with the active CTX for the example. So we have to go through the whole pool of characters first before we do a comparison with ESI, which we can see there. No, there. So, you know, the ESI is stuck there, and we've got the final hash output, which is in EAX from the looks of it. Yeah, because EDX and EAX interchange, so EDX has, yeah. So they don't, so then we jump back into, we don't jump in there, do we? No. We add 4 to, so we move 4 along, as I say, because of the hash is 4, and we increase ECX, which is, I'm assuming, the counter for how much address of names there are, and then we continue on a merry way. So we are simply just exhaustively searching the address of names, or these, to simply find the ones that we want from the hashing. So if I now move to what happens if we do move, we go into this breakpoint here, which is pop ESI. So we go there. This is now EAX is C0 D6 D616. What is in ESI? That is the actual value for that's the actual value from the file, a binary. Actual breakpoint here is why I've got it breakpointed, will after this transformation be the API call that we want. So ESI now finally moves into EAX, and EAX, there we go. So we've got the close handle there, that is the hash there. Essentially it's using a novel way to load API calls, because we aren't decrypting in any way. We're actually using a set size transformation to simply get our API calls, essentially. Sadly, it's 22 minutes in. It's been a long time, but hopefully you guys found it interesting enough. And maybe I can do something else about H1N1 loader relatively soon. It's been an interesting one. Hopefully you guys enjoyed it, as I say. And yeah, thank you very much for watching. See you later, guys.